So we've looked at simple interest. Now we are going to look at compound interest. Now the difference between compound interest and simple interest is that unlike simple interest, which is purely based on the principal, the initial amount, so interest is earned on the initial amount, compound interest actually takes into account both the principal and any accumulated interest from the previous periods. Right, so the value of the investment grows faster from year to year, and so does the interest amount. So the amount of interest is growing each year because it's taking into account the amount of money at each period that is within that balance. Now, simple interest was linear growth. Now we're looking at geometric growth. So the rule we use for compound interest can be seen just here. So as you can see, v of naught is still the principal, and the next term is equal to r times v of n, where r is equal to 1 plus r over 100. All right, so that's our rate. So let's have a look at an example. So the following recurrence relation can be used to model the compound interest investment of $2,000. So that's our V0, paying an interest rate of 7.5%. So that is R. Now, that's not the big R, but remember that this here is R, capital R, and this R comes into play when finding this value here. So this value here was found by going R equals 1 plus R over 100, and we know that R was 7.5, so we're going to go 1 plus 7.5 divided by 100, which is going to give us 1.075. So that's how we found R within our formula. So the question says, in the recurrence relation, Vn is the value of the investment after n years. So use the recurrence relation to find the value of the investment after 1, 2, and 3 years. So we've given the recurrence relation up here, so let's write it out again. V0 is equal to 2,000, right? Where V of n plus 1 is equal to 1.075 times Vn. So V1, or year 1, is going to be equal to 1.075, just using the rule, times the previous term, which was V0, so 2,000. Alrighty, and put that in the calculator. We find that for year 1, we get a value of 2,150. Alright, V2, use the rule again, 1.075 times the previous term, which was V1, which is 2,150, is going to give us 2,311.25. Always rounding to 2 decimal places when working with money. Rightio. Now we need to find the third year. V3 is going to be equal to 1.075 times previous term, which was $2,311.25, which is going to give us 2,484.59. So this is the value after 1 year, 2 year, 3 year. So the next part of the question says, determine the value of the investment when it will exceed 2,500. So we're looking to find out when it will exceed 2,500. So we are going to put it in our Casio calculator. All right, we should be getting good at this. So put in the initial value, which is 2,000, and we know that from the question previously. And we know the rule, R was equal to 1.075. So put in the value and then multiply by 1.075, enter, 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 enter. And we can see that after 1, 2, 3, in the fourth year, all right, fourth year, it will exceed $2,500. So the fourth year. Okay, so part C says write down the recurrence relation if $1,500 was invested in a compound interest rate of 6% per annum. Right, it's asking us to create the recurrence relation. Right, we're talking compound interest, so remember it's going to take the form of V0 is equal to our principal. We know that that's 1,500 Alright, where v of n plus 1, the next term, is equal to r times vn, where r is equal to 1 plus r over 100. Nice. So we need to find r using our formula. 1 plus r is our interest rate, which was 6%. 6 divided by 100 is going to give us 1.06. Lovely. All right, let's write that into our formula. V of naught is equal to 1500. And V of n plus 1 is equal to 1.06 times Vn. Lovely. All right, so this example is a really important one. So now what we're looking at is different compounding periods. All right, what we've seen so far is where the interest rate is applied, say, 6% per annum, compounding per annum. Now what you're going to see, or start to see, is that the interest rate might be 10% per annum, but it's compounding monthly, or it might be compounding quarterly, or it might be compounding half yearly. So there's lots of different compounding periods, and when we have different compounding periods, it is going to change the value of our R, all right, or our rate. So let's have a look. You remember that V of naught equal the principal, where V of n plus 1 is equal to R V n. Alrighty, so you'll remember that R equaled 1 plus R over 100. That's correct, but we're going to take it the next step now. From now on, you're going to consider R as R equals 1 plus R over n over 100. Right, so that's R divided by n divided by 100. But what is n, you ask? Very good question. So n is the number of compounding periods in a year. Right, so if it's yearly, the compounding period, well, there's only one. If it's quarterly, there's 4 quarters, 4. Right, if it's half yearly, it's 2. And if it's monthly, it's 12. Let's have a look at an example. So Brian borrows 5,000 from the bank, so that's his V of naught. He will pay interest at a rate of 4.5% per annum. Right, so let V of n be the value of the loan after n compounding periods. Write down a recurrence relation to model the value of Brian's loan if interest is compounded. All right, we're going to firstly look at yearly. Now, this one's quite simple, but we're going to progress to some different ones. All right, so remember our rule needs to take the form of the above, where it was V of naught equals the principal, and then Vn plus 1 equals R Vn. So we know the principal, that was 5,000, as we've got over here, which I entered in earlier. But we need to figure out the rate. All right, so the rate is going to be 1 plus, what was our interest rate? 4.5 divided by the number of compounding periods, which was, well, it's yearly. So there's 1. And then divide that by 100. All right, put that into our calculator. And we get the rate to be 1.045. Sub that in. So therefore, V of naught equals 5,000. Vn plus 1 is equal to 1.045 Vn. Cool. So looking at the same information, we saw that Brian put $5,000 into an investment account at 4%, 5% per annum. Now, previously we got a recurrence relation, but now you're going to see how when it's compounded differently. Now we're looking at quarterly and monthly rather than yearly. You're going to see how we gather a different recurrence relation. Remember, V of naught equals the principal, V of n plus 1 equals V of n. Alright, so here, we're talking quarterly. There's 4 quarters in a year. That's the number of compounding periods. Alright, so we know V of naught, 5,000. Let's find R. 1 plus R, our rate was 4.5, divided by the number of compounding periods. That's this n. Alright, it's 4 divided by 100 equals 1.01125. Sub that into our formula. So therefore, V of naught equals 5,000, as it was in the last recurrence relation, where V of n plus 1, here's the difference, 1.01125 Vn. Now we're going to look at C, monthly. How many months are there in a year? 12. So there's 12 compounding periods. So now we're going to sub n in, or 12 in, as n. Alright, this is something you need to be really careful about, because it'll come up a little bit, and you need to make sure that when you're finding your R, that you're subbing in the rate and the number of compounding periods correctly. Alright, cool, let's continue. R is going to be 1 plus, well, it's 4.5 again, divided by the number of compounding periods, which is 12 because it's monthly, divided by 100. We are going to get 1.00375. It's different to our last one, isn't it? Awesome, because it's compounding more regularly. Alright, so let's sub that into our formula. We have got V of naught is equal to 5,000 again, as it was for the last one, where V of n plus 1 is equal to 1.00375 Vn. Really important skill, alright? So R, you need to recognize, is 1 plus R over the number of compounding periods over 100. Fantastic. This is for compound interest. The R will change to be a little bit different when we look at depreciation.